Now let's consider all the chemical reactions that are occurring in a buffer solution. So we have an acid. I'll just use some general acid form, HA. And its reaction in water, and we call this reaction and its equilibrium constant K sub A. And we have a base. I'll use the conjugate base for this acid, A minus. And we'll call that KB because this is the conjugate base. So it has an equilibrium, and if we added these two reactions together, you can see that A minus will cancel, HA will cancel, and we will just get 2H2O giving H3O plus and OH minus. This is the KW equation. So if we have Ka times Kb, and if these are acid conjugate base or base conjugate acid pairs, then their product is equal to Kw. If I add reactions, I multiply their equilibrium constants. So if we know Ka, we can find Kb for its conjugate base. Or if we know Kb for a base, we can find Ka for its conjugate acid by knowing Kw, and this is just 10 to the minus 14th. It's a constant. Okay, now let's consider if we have a mixture of an acid and its conjugate base. So now we have a buffer solution. So say we have an acid. HA, and we have its conjugate base, A minus. So we have both of these in solution. So now say we add some base, strong base to the solution. What is it going to react with? Well, it can react with the acid. So the acid and the base, so we add strong base, so we're producing OH minus from the addition of the strong base. And if we look at this reaction, the acid and the strong base, we could form A minus plus water. So that's a possible chemical reaction. Well, let's look at this reaction in detail. This is the same thing as the conjugate base reacting with water to produce the acid and OH minus. So this is just the backward reaction for the conjugate base. So this equilibrium constant is equal to 1 over Kb. I'll just call this K1. So Kb is usually small. So say if we had something close to acetic acid or hydrofluoric acid, say the Ka is 10 to the minus 4th, the Kb would be 10 to the minus 10th, and 1 over Kb would be 10 to the 10th. So that means that this equilibrium constant is very, very large. So this reaction goes almost all the way to completion. So the reverse arrow is really small. So this reaction goes mostly to the right. So this way, if I add some strong base to a solution with acid in it, it will react to give the conjugate base. Now, say I have the conjugate base also present in solution, and I add strong acid. Strong acid will produce H3O plus in solution. So now the conjugate base and H3O plus can react to give HA plus water. So you'll see that both reactions are producing water, and I'm taking the acid and forming the conjugate base, or the conjugate base and forming the acid by the reaction of strong base or strong acid. Now, if I look at this reaction carefully, it's just the reverse of the Ka reaction. An acid in water produces H3O plus and its conjugate base. So this is just the backwards reaction of a weak acid in water. And so this equilibrium constant is just 1 over Ka. Now Ka is usually small, so so if I have Ka, which is 10 to the minus fourth, that means K2 will be 10 to the fourth, or 10,000. So this reaction has a large equilibrium constant. So this is what will happen in solution. So these two reactions predominate in solution. So we have a buffer solution. If we add strong acid or base, these two reactions predominate because their equilibrium constants are large. So this way, the strong base or strong acid can be consumed, and we just produce a little bit more of A minus or HA. We already have a lot of that present in the buffer solution, so we just produce a little bit more for the consumption of strong acid or strong base. Now we can overwhelm the buffer system. If we add too much strong acid or strong base, then we overwhelm the buffer and we produce too much of this, and we can't keep the pH constant. But for small amounts of strong acid, strong base, the pH will remain relatively constant.